please, these two equations try to make an effort to learn by memory because they are important. They are similar, it's not so difficult to learn by memory. A third objective function could be the correlation coefficient. You don't need to learn this by memory for now. For now, because I say for now because we will consider the correlation coefficient later on. And let me see, because there are some symbols here that are not... this is the estimated x, so this is like the symbol here. And the same here, this is the mean of the simulated. So basically here you have the observation, observed, minus the mean of all the observed value, times simulation minus its mean. And at the denominator here you have the standard deviation of observation and standard deviation of simulations. Maybe that in PowerPoint it is correctly visualized because I opened with LibreOffice. I think in PowerPoint it can be correctly seen. I assume that you know what is the mean of a series of values, and I assume that you know what is the standard deviation. If you don't really remember how it's computed, you can just Google deviazione standard or standard deviation and you get to Wikipedia. There is a very simple formula. I'm not recalling all these concepts because, you know, it's otherwise I become too pedantic. There is one important thing to say of, first of all, of the correlation coefficient. This is what we can say a very lenient objective function. Lenient means the opposite of strict. Meaning that, you know, you can get a very good correlation coefficient even if the data, the performances are not really the best. So for this reason, this objective function is rarely used. It's very, again, very lenient. Second important thing, these are all squared objective function, meaning that the errors here are squared. And even here, you see that there is a product. Let me see, because this square here is a mistake. Sorry, I didn't notice it before. I'm going to correct on the PowerPoint, but for now, please note that this is a mistake. This should be eliminated. So please take a note, especially if you just downloaded the file. But in any case, this is a squared measure. It's a squared measure because you see that there is a multiplication. X here is multiplied by itself. So this is again a squared measure. You see that observed and simulated are multiplied. And even in these two is more evident that we have a squared measure. The error is squared. What does it mean? So what do you obtain if you square the errors of the observation, which is the same? You give more weight to the highest values. So if you have two errors, one big and one small, they already differ. But if you square them, the difference becomes much and much higher. So this means that if you have just two errors, you give more weight to the higher one. Therefore, basically, given that you have the highest errors for when you get the highest observations, because of course, if you are during a drought period, then you don't make a big mistake because the flow is so limited that you don't make a big error. But when instead you have floods, which means that your flow is maybe 10,000 bigger, 10,000 times bigger, then you make bigger error. And therefore, if you give more weight to the biggest errors, It means that you are focusing on floods. It means that you are optimizing the performances of your model with particular reference to floods. And this is something that we have to keep in mind. If you want to use our model for making flood prediction, this is good. Because we are focusing on model performances during floods. But if we want to use our model for drought prediction, low flow predictions, drought is magra in Italia, then this is a problem. Because the model becomes good in reproducing floods, but we don't have any assurance, any clue on model performances during droughts. So of course people started complaining on this and said, okay, but if I want to focus on drought, then I should use a different objective function. So what kind of objective function should I use? So here is the reply. For instance, the mean relative error, which is not a quadratic measure. Then you take the difference between observation and model simulation, you take the absolute value, you divide by the observation, and then you take the sum. This kind of objective function, you just should be a bit careful because it may become unstable for very small values of xt. Because of course, if the denominator tends to 0, then you have the objective function that tends to infinity. So it becomes a bit unstable. So we should be careful to this. And there are variants to avoid this problem. For instance, one variant is to apply the summation at the numerator and denominator separately. There are many and many other objective functions. I don't spend more time on this. And you can also devise your objective function depending on your experience and depending on the modeling purposes. So if you have a particular purpose in modeling, then you can define your specific objective function. I just would like to remind you that the task of this objective function is to provide to the PC a measure of model performances. And then what the PC does is to change the parameters to identify by trial and errors the parameters that minimize or maximize, let's say optimize these objective functions. Good. So, some problems. And first of all, let me mention a problem that is not mentioned here. And the first problem is computational requirements. We are talking about a task that is done by the PC, and of course it takes time and takes computational resources. And you know, when I said that there has been in the last 20 years a relevant research activity on this subject, it is because this research activity was aimed to find out, to set up algorithms that were computationally efficient. Because it may take to calibrate a model with many parameters, because we had experience so far with a model which is iMod that counts 5 parameters, but there are models that count maybe 50 or even more. So if you have to calibrate so many parameters, it may take a couple of weeks to the PC to perform the optimization. And therefore, of course, it's important to possibly develop algorithms that are efficient. So the first problem is computational requirement. And then here we have a list of problems that I would like to go through. First of all, overfitting. What is overfitting? Overfitting occurs when you introduce many parameters, and therefore, when the number of parameters with respect to the observations becomes significant, what can happen? First of all, you know already that you need a minimum number of observations to estimate a parameter. Let's think to the slope of a straight line. You need at least 2 observations. If you have just one, you cannot estimate the slope of a straight line. This means that there is a relationship between the number of observations and the number of parameters that you can estimate. And even if you have 3 points to estimate the slope of a straight line, you understand that the uncertainty is very relevant, because you know, if you have an uncertain linear regression like xt and fxt, and then you have just 2 points, then you say, okay, I'm done. I want to estimate the slope. This is my estimate, which is perfect, because I have just 2 points. But then, if you get a third observation, maybe here, then you say, okay, I can change. And then you get this estimate. And one may say, okay, I'm fine, because I have more observations than required. But then the fourth one may be here. Which means, and then the slope changes again. Which means, and then you may understand that when you have 100 points and you get one more, it doesn't change much as the slope. The slope changes much at the beginning, but then when you have a huge number of observations, then you are really done, because the slope doesn't change much if you had just 1 or even 10. So this means that the more the number of parameters is lower than the number of observations, and the more you are happy, the more your estimation is reliable. So you understand that your estimation becomes much more reliable when the number of observations is much higher than the number of parameters. Now, let's go back to the case of just 2 points in linear regressions. Let's suppose that we are not aware of this problem, and then we get 2 points. And we are not aware of this problem, so we fit our linear regression model, and we get a perfect model. Of course, because we are able to reproduce these 2 points perfectly. And we may say, if we didn't know the problem, we may say, I have my perfect model, I can make a prediction which is certain. And then, if you want to predict a third point, you could, for instance, in the future, you could say, okay, this is my prediction. And I would say it's a perfect prediction. But then you get your observation, which may be here. And then your prediction turns out to be wrong. And this is a very nasty situation, because you were convinced that the model was perfect. This is overfitting, means that the number of observations is too small with respect to the number of parameters. And the problem is that you, in principle, don't know how many observations you need. For instance, think at high mode. You have 5 parameters. How many observations do we need not to have overfitting? We don't know. So this is overfitting, meaning that you calculate a model, you could get the feeling that the model is very good, and when you go to apply the model, you realize that it's not good at all. because the number of parameters, again, is too high with respect to the number of observations. Good, this is one problem. So we have to avoid overfitting. And how to avoid it, let's see later on. Second problem, what is called equifinality, which is related to overfitting. Equifinality means that you may find for your model two or more parameter set which gives to you the same performances. So you may see for iMod two parameter sets, completely different each other, but then when you look at the comparison between observed and simulated hydrograph, they look the same. So what set should I choose then? This is equifinality, means that you get similar model performances for different parameter sets. And you are more likely to get equifinality when there is overfitting. Okay, let's move forward. Correlation among parameters, this is a bit of a problem, which is not really easy to explain. When you have, but I try, when you have many model parameters, it may happen that they are correlated. What does it mean? It means that you have compensation among parameters. So if you have the first parameter that gets a wrong value, then the other parameters get an equally wrong value to compensate, meaning that there is interrelation between parameters. So let me make an example. Let's suppose that in iMod I erroneously estimate a very small storage capacity in the catchment. It's an error, which means that the real catchment can store more water. The modeled catchment instead doesn't keep water. What happens then? That you have the first parameter that is wrong, low. Fine. What happens? If you put rain into the model, you have the real catchment that gives a much lower response than the model. So, let me try to make a sketch. So the case is iMod, and you get Cmax that is wrong, and then it's lower. Okay? What happens? Okay, then you apply your model. And then you have here the rainfall that you put in input in the model. So this is your PT. And this is T. Let's say that this is in rainfall intensity. And then you have your rainfall. Okay. Let's look at the hydrograph. QT depending on T, and then you get this kind of hydrograph observed. So you have an increase and then a decrease, and then again you have this observed hydrograph. Then if you look at the model simulation and Cmax is wrong, you have an higher hydrograph. So something like that. Why that? Because your model stores less water than the catchment, and therefore you have much more river flow. Then as a consequence you will see, this is not really correct, at a certain point you will see that of course the observed hydrograph goes upper the simulated one, because for continuity, if you have more water before, then you have less water after a while. Okay, now what may happen? If you remember in IMOD, then you have two storages given by the linear reservoirs, which is a chain of linear reservoir for surface water and just one linear reservoir for groundwater. So what may happen in the attempt by the calibration process to compensate for this error is to decrease the two constants k, which were called, I don't remember, one for the surface water was probably QS and KG, something like that. No?
QS and KA.
Okay. If you decrease this, decrease or increase, it was a denominator, I think it is an increase. If you increase these parameters so that you store more water in this reservoir, you compensate and you bring the simulated hydrograph closer to the observed one. So basically you make a mistake in the estimation of Cmax and you compensate by increasing these numbers. I don't remember in my slides if k has the dimension of a time or the dimension of 1 over time. If it is 1 over time, okay, so it's a decrease. If you decrease these parameters, then you store more water in the linear reservoirs. So you compensate the lower storage in the catchment with a higher storage in the two reservoirs. And this means that these parameters C and the two K's are related to each other. So if you decrease C, you also decrease the two K's. This is correlation among parameters. It's a bit of a problem. In hydrology always happens, but it's a problem because it leads to equifinality. So you have different parameter sets that give the same performances. And be careful, you may say, I don't care. If I have the same performances, I take one parameter set or the other one, and I don't care of the difference. You can't say that, because the equal performances are in calibration. When you run the model in application, the two different parameter sets give two different outputs. So it's only in calibration that you get similar performances. You are not guaranteed, you are not sure that you will get similar performances also during application. So correlation among parameters, which leads to equifinality, and equifinality is also caused by overfitting. It's a problem. So, what's the solution here? The solution is the solution to overfitting, to equifinality and correlation among parameters is, for instance, and I jump one line, to use more than one objective function, because any objective function looks at a specific behavior of the hydrograph. If you use two of them, you look at different behaviors. Like I said, least squares looks at floods. Mean relative error looks at droughts. So they look at different behavior. If in the calibration you use more than one objective function, you may solve the above problems. This is called multi-objective calibration. I'm not spending any time on that because it's a very complex topic, but you have to know that it exists. You have to know that you can consider more than one objective function, because this is, in application, this is done very frequently. And if you apply multi-objective calibration, I go back to the previous line, basically you are using more information. In a way, you have an observed hydrograph, which is your term of comparison. When you use an objective function, you are trying to synthesize the information given by the hydrograph. So when you compute the least squares, you are getting information, you are synthesizing the information that the observed hydrograph gives to you. But in doing so, of course, you are converting a lot of information given by an hydrograph. An hydrograph really tells you a lot. You are condensing all this information in a number, least squares. So it means that you are, in a way, synthesizing, but while synthesizing, you are losing something. If you use two different objective functions, you are losing less. So this is why here I wrote need to use all the available information. Let's don't assume that least squares, or in any case, a single objective function can extract all the information from an hydrograph. No. There is more information. And if you use multi-objective calibration, this is an opportunity to extract more information. Now, the last line is a detail of multi-objective calibration. When you have multi-objective calibration, then you enter into a class of techniques, which I already mentioned, it's multi-objective calibration, which is very extended. And I'm not going into these details, so you may forget this last line. I just put it in because this term, which you see here, the Pareto frontier di Pareto in Italia, it's a term that is often encountered. And I don't want to dedicate 2 hours, because it would take to me 2 hours of explanation to explain to you what is a Pareto frontier. I don't want to do that, because it would be too technical for the purpose and the broad focus of this course. But I just want you to know this term, and to know that refers to multi-objective calibration. So when you heard someone talking about Pareto frontier, then you know that refers to multi-objective calibration. And if you want to know more, just go to Wikipedia and look for Frontiera di Pareto or Pareto frontier, and you get the information. Basically, what it means is that when you use multi-objective calibration, you don't have a single optimal solution. You have a set of optimal solutions. And this set is lying geometrically on a region that is called the Pareto frontier. The reason why I make a break of 1 minute, the reason why sometimes I introduce these terms and I say there is no need for you within this course to learn them, but I want you to know them, is that in your professional activity, or in my case, in my research activity, or even teaching activity, there is nothing more uncomfortable when you speak with a person, when this person uses a technical term that you don't know, and you realize that for this person it's a technical term that is like the bread that we eat every day, and you don't know what you have no clue of what is. This is a very uncomfortable situation that I experienced many times. So I thought it's better that I introduce to students the technical term that in my experience were more frequently used and put me in an embarrassing situation. And this was the case for me for the Pareto frontier. I realized that people were talking about this Pareto frontier, and also 10 years ago it was not so easy to get information. Now with the smartphone you go to Wikipedia and you get information. 10 years ago I had to go to the library and look on the web. There was not much information. So basically I think that sometimes, even if I don't go into the details for the technical terms which are more used, I think it's useful if I mention them to you. So this is why I'm not going in a detailed explanation, but I wanted to mention. Now, let's move to validation. So far, we just talked about parameter estimation. And I already mentioned to you that the fact that you get good performances in calibration doesn't automatically imply that you get in validation the same good performances, not in validation, in application the same good performances. So it may happen, and indeed it happens quite frequently, that you experience overfitting, and therefore you get very good performances in calibration, like this straight line connecting 2 points, and so you get confident in your model, but when you go to apply your model, then you realize that the model is blatantly wrong. Okay, then how to solve this problem? And the idea is to try to check the model by emulating an application before the actual application. Therefore, if I plan to use the model, for instance, for flood forecasting, in order to warn people whether or not they have to leave their houses and so on, the idea is, let me try to simulate an application, to emulate an application. So let me try to refer to a past flood event and try to predict it, like if I had to predict it right now. So this is the idea, to put ourselves in a context which is in all similar to an application, but of course it's not an application. Is something which is in between calibration and application. And this something has been called validation or verification. And it must be very clear that if you want to emulate an application, you have to assume that you are operating online. So you have to get data referred to a flood event, for instance, and pretend that you didn't know this data. So basically, if you want to try to predict a flood that already happened, of course this doesn't make any sense. Prediction by definition is when you try to obtain information on something that is in the future. If you refer to something that already occurred, this doesn't make any sense. So you have to assume that you didn't know that it occurred. You put yourself in a situation where you don't know anything, you just know rainfall, that is raining. You get this rainfall raining. This is the only thing that you can assume that you know, because this is what you know in application. You usually know rainfall, you are measuring it. But you have to assume that you don't have any information on the river flow. Now, what is the implication of this? The implication is that the set of data that you use to validate your model must not be used in calibration, because this is a completely new situation. You want to, if the data were in the future, you wouldn't use them for calibration, would you? No, of course, you don't have the data. So if you want to really validate the model, to really emulate an application, you have to get a set of data which you didn't use in calibration. This is a very basic but unquestionable principle. The data that you used in calibration cannot be used for validation. Okay. Look, out of sample. Out of sample is what I mean to say. Out of sample means data that were not used in calibration. Then, this is what happens. You use a technique that is called split sample. So you call sample the pool of your observed data. You split it. A part of the sample is used for calibration, and the other part of the sample is used for validation. Split sample. Okay. There is a problem with the split sample technique. The problem is that very often we don't have large samples of data. And therefore, if we split the sample, we get in a situation we have even a smaller sample of data. So some people say, what's the purpose of doing this? It's not useful, it's not efficient. We have a reduced amount of data in calibration, we have to use all this data. Okay, but there is also the need to perform validation. So one possible solution is I split the sample, I calibrate the model and I validate it. Then, once I got the confirmation that the model is good, I recalibrate the model by using all the whole sample. So basically the split sample is only for making the verification. Then, once the model is verified, I recalibrate it by using the whole sample. Of course, the critic that is done in this case is, okay, but the model that you verified is not the model that you apply, because if you change the parameters, the model is no more the same. So the verification refers to a different model, not the one that you are applying. Okay, fine, but in any case, it's better to do so than to avoid verification at all. So I know that the verification is not really representative, the validation, but still, it's an indication. Okay. Or there is another technique which is increasingly used, which was more computer intensive, and it's jackknife validation. What does it mean? Suppose that you have a sample of data, and let me refer just to the hydrograph for now.